I want to welcome you to our seminar Parameter Identification with OptiSlang. I'm René Kalmar from Dynardo and I want to lead you through this webinar. In this seminar, I want to show you how you can use OptiSlang for model updating to get some optimal fit between some simulation curve and some measurement curve, or maybe some curve for some desired behavior. In order to perform such a model calibration, you must be able to work with non-scalar values like vectors, signals or matrices, and not only with scalar values. And you must define the right optimization goal you want to minimize. I will show you in the following slides why is OptiSlang the tool you need for this model calibration. And at first, I want to give you some overview what we're going to do. At the beginning, I will talk about the theoretical background of this parameter identification. What does this parameter identification means? And afterwards, I will say something to the process integration of your simulation environment and also of the sensitivity analysis. The next point will be the least square minimization. And finally, you get some information about an example or two examples where we see the whole identification process. First, we start with the theoretical background. What does parameter identification means? If you have some simulation model consisting of some parameters, maybe some material parameters, geometry or boundary conditions, then you want to estimate these parameters for some real application. And in order to estimate these parameters, you can do some measurement. And in some cases, you can really directly measure these parameters, like material parameters, for example, Young's modulus. But in more complex situations, then you need to do some inverse procedure, where you compare the simulation results with the experiment results. And the aim of this is that we want to obtain the optimal model parameter set to get the best comparison between your simulation and measurement results. And this can be done with such a so-called forward simulation. Therefore, you need some simulation model with model parameters P1 until Pm as some input parameters, and we modify these parameters in order to obtain such model responses y1 until yn. And these model responses we can compare really with the measurement y star 1 and so on. And the measurement y star 1 are given from the experimental setup, and these are really constant during the whole identification procedure. But the model responses may change when we modify the model parameters, and the question is how we can obtain an optimal model parameter set which gives us the best agreement between these model response curves and measurement curves. And for this purpose, we can apply a so-called least square minimization. This is based on such a maximum likelihood approach. And in this approach, we assumed a correct simulation model, which means that the simulation model can build up really the physical behavior of an experiment. And based on this assumption, we can go further by assuming that the remaining deviation we have between this measurement and simulation is only based on measurement errors. And the next assumption is that we have a normal distribution measurement errors, and we assume also that the measurement errors are independent. And then the formula gets simplified and we get such a sum of weighted squared errors. And the last assumption is that each measurement point has some constant standard deviation, and with this For assumptions, we simplify the formulation to the sum of squared error. And this sum of squared error will often use. The simple function can be used in a wide range of nonlinear simulations, but really remember this formulation of sum of squared error is with help of 4 assumptions. But for real-life applications of this least square minimization, we have to fulfill some requirements. First, we must be sure that the main physical behavior of the experiment is really represented by the simulation. That means that maybe some systematic model errors in the experiment cannot be considered in the identification procedure. And second, this identification procedure based on this least square minimization will lead to this previous shown objective function before, and this has to be minimized. And this maybe have some several local optima, and therefore we need in the most cases an optimizer which has the possibility to find really the global optimum, not some local optimum. And third point is we can only identify sensitive model parameters. That means if some model parameter has no influence on the model response we compare with the measurement, then theoretically the model parameter can take really each value between your lower and upper bound. And so we have first to check which are the sensitive parameters with respect to the responses, and this can be done with the help of our sensitivity analysis. And then we do the identification procedure only with the whole sensitive parameters. Here you see the flowchart of a model calibration, and if we want to have the best fit between curves, we must use our signal processing. That means you can use with this help of signal processing some non-scalar values like signals, vectors, or matrices in your simulation environment. In the identification procedure with OptiSling we're talking about today, we're using the sensitivity analysis in order to get information about important parameters with respect to the model responses. And for this, we define such a design space with your defined lower and upper bounds, maybe for continuous and also for discrete parameters. And after the sensitivity analysis is finished, we have to check the parameter bounds for every parameter if they are correct. That means we have to check if the bounds we have chosen are suitable for the response function. And if it is right, we can continue with the optimization. And the following optimization needs a defined objective and the right parameter bounds to find the best fit between your reference curve and your simulation curve. And you have seen, in order to perform such a model calibration, you must be able to work with signals and not only with scalar values, and you must define the right objective for the optimization, and I will show you how you can use this in OptiSling. But before you start with sensitivity analysis and optimization, we must connect your simulation environment to our software OptiSling. That means we need to have some process integration. And the first step for this is that we have to build up a model. That means we need a parametric model. You must define design variables when you want to do some sensitivity analysis or optimization. And if you want to do some robustness evaluation, you must define some scattering parameters. And with the help of these input parameters, you have to define a design space through lower and upper bounds of your input parameters. Those parameters are for the system, the CAE process, and the COE process includes your solver, maybe, and this workbench. And at the end, we will obtain response variables as outputs, and these response variables can be some scalar values, some vector, signals, or matrices. Here you can see many integrations which are available in OptiSling. And in this way, you use OptiSling as an integration tool to automate your process you define. And there you have two ways of integration. First is the direct integration, mostly known as the ANSYS Workbench node, but also we have MATLAB or Excel as some direct integration. On the second way, we have the text-based integration with easily exchange of text files, and the most general connection is the common text-based integration, where we connect to every text-based solver, and it doesn't matter if it is maybe CFD or some finite element solver. Another integration is the product ANSYS Workbench OptiSlang plugin, and in this ANSYS Workbench OptiSlang plugin we have the modules sensitivity, optimization, robustness, and signal processing, which are simply connected with the parameter set by drag and drop into the project schematic of Workbench. And if I had said before that the outputs you get as response from the solver can be scalar values, vectors, signals, or matrices, but in our special task, this parameter identification, we want to extract signals coming out from the simulation, maybe some force displacement curves, or maybe some displacement over time. And on the other hand, we have some reference curve coming from the measurement. And signals in OptiSlang are only some outputs with some abscissa axis and some ordinate. And so you can also say curves instead of signals. And after having signals from simulation and measurement, we want to compare the simulation and reference curve. We can interpolate the points of simulation with respect to the points of measurements, and then we compare both of them, for example, in this using sum of squared error. And to work with the signals, we have this module signal processing in OptiSlang and also in ANSYS Workbench OptiSlang plugin. The signal processing from the Nardo gives you really the first time the possibility to work with signal or curves in ANSYS Workbench and not only with some scalar values. And so you can really compare signals coming from the simulation with signals coming from measurements in order to perform such model calibration. Or when we extract some signals in order to get maximum minimum amplitude like this, or maybe some mean value, you can use also this one. The key feature of the signal processing is that it does not need some equidistant time axis or abscissa, so we get signals from simulation having some different time steps, and we can compare them in some optimization. And also it plays a role if you extract your curves from some txt file. We can also extract these curves from the binary file like file RST with some things I can show you in this live demo. Now I want to make a view to the sensitivity analysis, because we must identify parameters who are important for the model responses, and we want to filter out really the unimportant parameters we found in the simulation. So we defined the model with the input parameters P1 until Pm, and this will put to the algorithm design of experiment. That means we generate with respect to your defined lower and upper bounds variation of the input parameters, and put each design point, each dot, to the solver and get the results back from the simulation environment. And then we do some statistical analysis of input and output relations, and so we can scan the design space and calculate all the input and output relations. And after this, the MOP, this meta model of optimal prognosis, is automatically generated. The question is what the MOP does. The surrogate model describes in some analytic way the behavior of input and output relations. It goes through the whole number of possible regression models we have in OptiSlang, fits them, and compute the prognosis quality, the COP, of each available model, and it comes out with the result of the best available meta model we have. And this is one of the optimal prognosis quality. The MOP does some other important step. It found out which of the input parameters are very important for the model results and which not. And you see here with the ranking which are mostly important and which are less important. And so we come out with a set of most important input parameter, the unimportant parameters filtered out automatically, and we get a ranking which shows the really most important and less important parameters. And so we get really from the MOP 3 important results: the best variable subspace, that means less important parameters filtered out. Then we get the best meta model, and we have some estimation of the prediction quality, the COP value. And then the final step in the identification procedure, we started with the least square minimization. When you think on your curve, you have maybe such a curve with some monotonous increasing abscissa. This can maybe represent some hardening or maybe also some softening curve of your material. And for this curve, you can use such a simple sum of squared error as some objective. But if you have such a hysteresis curve with some load and unload, you must first make some decomposition of your curve in some load and unload. Then you must have a look to the number of discretization for this load and unload. And additionally, you can use also some distinct points like the max force, the max ordinate value, or maybe also the abscissa value for the maximum ordinate value. And maybe you can use also the intersection with the x-axis in your objective you have to define. If you have maybe more than one curve for description of the material, you can also handle this during the optimization. And for this, you must have a look to the number of discretizations. For experiment 1, maybe some tensile test, and experiment 2, maybe some bending test. And you have to look also to the ordinate values and normalize the experiments. I have said before, we want to minimize the objective functions, maybe the sum of squared error. And for this, we have a wide range of optimization algorithms like these gradient-based method. These gradient-based method have the best accuracy if we can really compute some gradient. But if you have maybe some failed designs or numerical noise, this gradient-based method doesn't work for this. So for this purpose, we can use the RSM. But for some maybe global optimization, the PSO and evolutionary algorithms are quite efficient in order to really detect the regions of global optimum. And then we can use some RSM or NLPQL to come closer to the optimum, because the nature-inspired algorithms are not so accurate like this NLPQL or RSM method. And this combination of global search with some nature-inspired algorithms followed by some local search with RSM are also important for this procedure of model calibration. The decision you have to make for some suitable optimizer is often not so easy, but don't afraid that you have to choose these optimization algorithms for yourself. For that, we have such an decision tree. We suggested you some algorithm depending on the settings you made. That means you have to answer these 4 questions and you get some recommendation of us. If you have maybe some violate constraints, failed designs or solver noise. And with some simple traffic light plot, you see the recommendation of OptiSlang for the best optimizer and then start the optimization. Now I want to show you some examples of model calibration with OptiSling. And here you see some list of possible tutorials and examples we have for this model calibration. First one is some curve fitting by variation of geometry parameters for some press contact, or some optimization of material parameters of some spring steel for some best fit. And also here you see some optimization of material parameters for some sandstone on concrete to get the best fit between measurement curve and simulation curve. And also here you see some examples. The first example I want to describe is press fit contact. It means is some example in ANSYS Workbench where we have two components. This first component will insert into the second component, and that means we have some variation of geometry parameters, and we extract the reaction force as some force displacement and get the insertion force and the pull-out force for this component. That means we have some insertion force maximum, we have some gradient for this insertion force, and also for the pull-out force we have the same. We have some gradient of the pull-out force and some max pull-out force. And now we have a reference curve not coming from the measurement. This red reference curve will be maybe come from your salesperson, from some customers, and so you have some desired behavior. That means maybe you want to have some smaller gradient for some insertion. Maybe you want to have some smaller maximum insertion force, but for the pull-out force you want to have a maximum of pull-out force, and also maybe here some higher gradient to this pull-out force. And so here you use the reference curve, not from some measurement. Here this reference curve will build by your desired behavior. And you want to know which geometry variation of these two components gives you the best fit between these two curves, between your simulation curve and your desired behavior. The second example is a tension test of a tensile bar of spring steel. That means you have some fixation in this area A and some displacement in this area B, and you have some force displacement curve coming from your experiment. Here you see in red your reference curve. You make some simulation and you get some initial curve from your simulation, and you want to get a best fit between these two curves. For this you make some variation of these parameters. This is the description for the full plastic behaviors. It means you have some yield stress, some linear hardening coefficients, some exponential hardening coefficients, and the saturation parameter. These four parameters describe the whole plastic behavior of the material, and we use also the Young's modulus. So with 5 parameters we can define the whole material behavior of this spring steel, and we use these sum of squared error as some optimization goal, and we want to minimize these. Here you see this description in this workbench. We have some geometry, we have the static structural simulation of this tensile test. We use this signal processing to read in the reference curve coming from your measurement and read in the simulation curve for every design step, and we can use sensitivity and optimization to minimize these objectives. Here you see we described this material with some APTL snippet. That means here you can see also APTL snippet is used as parameter definition, and here you can find in the parameter set which parameters we have in ANSYS Workbench, input and output parameter. In the signal processing, we put on the done solution, we can import some reference txt file, for example, and in this reference file we can define our curve as some signal, our reference signal. After this, we imported some file RST. That means with help of this binary format file RST, where we can define our output signal coming from simulation, but it's also possible to define your signal simulation with help of some file of some txt file if you're writing it with or save it with APTL. And here you can see if we compare this signal reference, this is this blue one, we compare it with the simulation signal, we see we have not the same discretization and we have not the same length, and this is necessary for some model calibration that we have the same length and the same discretization, because it's not useful if maybe your reference curve will be extrapolated in some regions where you have no data. The next one is that maybe also for this insert force and this pull-out force, it is important to know in which area of the signal which input parameter have some influence, and therefore we divided our signal into equally spaced steps. In this way we choose 15 steps, and on these 15 equally steps we extracted the forces, and with help of these 15 force steps we know in which region of the signal which parameter have some influence, and these force steps is some vector, and we use this vector also to define our objective, and this objective with help of these vectors we want to minimize. Here you see the definition of the parameter, that means the parameter name, and here you see the range, the lower and upper bound of the parameters, and all parameters has some continuous range, not some discrete range. After finishing the sensitivity analysis, you can have a look to the results, and you see here the signal plot of this force displacement curve. In green you see this unique, this constant reference curve, and in gray you see all the simulation curves coming from the design points, and we see we have some full envelope of the reference curve. That means this is the aim of sensitivity, that we have really some envelope for the reference curve. If not, then we can't continue with optimization. We must start again the sensitivity with some other changes or some other values of the input parameter. Some other response of the sensitivity analysis is this MOP, this meta model of optimal prognosis for every response, and here you see the MOP for the response differences and also the two most important input parameter. And this response differences is the sum of squared error for the whole simulation curve, that means for all 35 discrete abscissa steps. And you see here also that for the response differences, we have some COP value nearly 100%, and we come in with 5 input parameter, and you see here only 4 input parameter are important for this response difference. And here you see on the bottom our COP matrix. That means on the ordinate you see some responses, and you see on the abscissa the input parameter, and the last column is the COP value, this coefficient of prognosis. And as what I said before, we divided our signal into 15 equally steps. That means we have some vector with 15 components, beginning with 4 steps 0 and ends with 4 steps 14. This you see here, each of these components for this 4-step sim, and you see also the response differences. And what you can see here, the single values of the 4 steps can be explained much better than the global difference, because here you have one meta model of the whole range from low to upper bounds, and here you have on some discrete point one meta model. And the next one is that this linear hardening coefficient is unimportant for this response 4 steps and also for differences. Because why? This linear coefficient describes the gradient at the end of the signal, and here you see all of the simulation curves has nearly no gradient at the end, and so this linear hardening are really unimportant for all the responses between these low and upper bounds. You see also that the Young's modulus is the most important parameters for these 3 first 4 steps. That means these 3 4 steps 0, 1 and 2 laying in this linear elastic behavior, and so it's clear only the Young's modulus plays some role, and by increasing the displacement, the influence of the Young's modulus will decrease. And here you see also that the influence of the yield stress and exponential hardening will increase with increasing displacement, and the influence of the saturation parameter are less important. The next step after this sensitivity is that we want to optimize the objectives. That means we define some objective and we use this MOP to optimize directly on this MOP. The advantage of this optimization on this MOP is that we have this analytical description of input and outputs, so we do not need some real solver core. We directly optimize on this MOP without some real solver core, only if you want to validate the best design. And here you see some result of the optimization on the MOP. If you have a look to the signal plot, this force displacement curve again, and in green you see the reference curve, and in red you see the best design of the optimization of the MOP, and you see the fit between these two curves is really good, and so you can decide that, okay, after this optimization on MOP you can stop, and it's not necessary that you run some optimization with direct solver cores with every time starting the solver like in this workbench. But if you want to do such a direct optimization, it is possible, like the simplex algorithms. And here you see some summary. If we make the sensitivity and having this MOP and make some optimization on this MOP, we get some final result of differences of 268 Newton. That means we make some optimization with help of this 4 steps vector. That means we make some optimization on these 15 MOPs and get some really good agreement between measurement and simulation. But if you want to get some really excellent agreement between these two curves, you can decide to start some simplex optimization to get some better result, but the difference between these 205 and these 268 are really small, and I will show you now directly in the live demo. Now we came to the live demo of this spring steel example. In ANSYS Workbench, you see here the whole model calibration with the model, signal processing, sensitivity, optimization on this MOP second time, and some diode optimization. Normally you started only with some container A and B and with this parameter set. And here you can see we have this tensile bar with some fixation and displacement, and under this geometry we define our material, this nonlinear isotropic hardening, and we see here in this APTL we can define some input parameter. And in this parameter set we find all inputs and outputs which are coming from the workbench and also from the signal processing. So after this done solution, you can easily drag and drop this signal processing to the solution like this one, and then you can open the signal processing. I will open this define signal processing. That means I will show you how we defined reference and simulation curve. That means we imported the txt file for the reference curve. You see here in this EDK this reference txt file, and here we define the whole reference curve coming from the measurement, and in this file rst we imported this binary file and we extracted the simulation signal. And in this variables tab we see here what I showed before in this instant visualization. We see here that we have some differences between this reference curve and the signal curve. That means reference curve is this blue one, and here at the end and also at the beginning we have some different lengths and some different discretization steps. Normally we define before this OptiSlang version 5.2 this difference as the objective. That means the Euclidean norm of signal sim and signal ref. That means we use the whole 35 abscissa values, and we use this difference normally as the objective. But now in the version OptiSlang 5.2 we have the possibility to work directly with this vector. That means what I said before, this 4-step sim and 4 steps ref are coming from a vector with 15 equally steps between these signal lengths from 0 to 1.75. This is the length of the simulation signal. Here you see the simulation signal, and we use these two vectors for this objective. That means if you define all these responses, you can close this signal processing, and we can then easily drag and drop the sensitivity to this parameter set. That means use the sensitivity and drag and drop to the parameter set. We connect it to this and extract the input and outputs, and here you find all the parameter names and the ranges. The ranges must be defined, maybe coming from the literature. In this way we define it in this way, 1000 to 1600. This is 1 to 1000, 400 to 900, 160,000 to 100,000, and this goes from 160 to 400. Only define the ranges and then you can go to next. Here you must define now your objective. That means now we define in the new version, this version 5.2, this objective by using these vectors. That means only type in objective. We want to define the type as some objective. And the expression is now we want to make the Euclid norm with help of these two vectors, 4 steps sim minus 4 steps ref. I want to make it a little bit bigger. Here you see Euclid norm with help of these vectors. You see here this 4 step sim is a vector and this 4 steps ref is also a vector. And we go to next. We define our DOE sampling. Also here you see the decision tree, and please use our recommendation with these 100 samples. Go finish, and the sensitivity will create on this workbench project, and after creation you can run the sensitivity. So now sensitivity is created, and so only with clicking update you can run this sensitivity. That means go to this triangle and click, and then you can choose update and run sensitivity. I made this before, and so we can have a look to the results of the sensitivity. That means you can double click to this result, and this sensitivity MOP UMDB is written. Here you see the meta model for all or for one of these responses, and here you see in this COP matrix on the ordinate you see the whole responses, and you see on the abscissa the input parameter. On the last column, what I said before, this is the COP value, coefficient of prognosis. It is clear that the 4 steps for the reference 0 to 14 are completely described by 100% because it is constant over the whole identification process. And here you see the 4 steps from the simulation. The first 4 steps are only influenced by the Young's modulus, and here you see by increasing of the displacement, the influence of the exponential hardening and the yield stress are also increased. And here you see the difference. The difference has also some high COP value, but the single 4 steps values can explain much better as these differences. And so we choose that we do not use this difference, this MOP of this difference, for some optimization on the MOP. We want to use every of these 15 meta models for some optimization on MOP, and this is the new one in 5.2, that we can use directly these 15 meta models to get some better optimization on MOP. So the differences between this optimization on MOP and maybe some direct optimization is closer, much closer. And so we choose make some optimization on MOP. These are done here, and you see here I will open it again. This optimization on this MOP. Here in this one I choose this criteria, what I said before, this Euclid norm between these two vectors. And in some second optimization on MOP I use the old version. That means I will show you again. We used the formulation of these differences. It means this Euclidean norm, or this sum of squared error for the whole signal. And if we have a look to these results, we can open the optimization on MOP. That means this is the one with this using of two vectors. We see here this difference has some value of 268 Newton. And if we have a look to this signal plot, only click to window data mining signal plot, a little bit this one. We choose that we want to see these two curves. That means in green this is the reference curve, and in red is the optimized design founding on the MOP. And you see the agreement between these two curves are really good. So this fit is really good for this optimization on MOP by using these vectors. And if you now have a look to this old version by using these differences, or this difference, that means we can open this one. And please remember, by using these vectors, we have some difference value of 268. Here you see the difference value are now 528. It is really a bigger value, 2 times more. And if we have a look now to the signal plot, you see really in the signal plot that the agreement, that the fit is not so good like using this other objective. Here you see this fit for optimization on MOP is not so good like using these vectors. Here you see some bad agreement in this region and also at the end of the signal curve. So we can say that by using these vectors, by using these 15 MOPs, we get a much better agreement, a much better fit for these two curves. And so you can decide if you stopped after this optimization on MOP by using these vectors. It means you have 100 design points for the sensitivity, and then optimization on this MOP with only one validated design. So you have in sum 101 designs. And if you have maybe more time, you can say, okay, I want to have some direct optimization like the simplex. But with this method, you have to start every time the solver. This means one design point will start the solver and one again. And you see here in this presentation this difference between this goal, this 205, between these 268 are not so high. And so I think this optimization on MOP is good enough. But if you want to have some excellent agreement between curves, then you can choose this direct optimization. And you can also do this in this workbench by drag and drop this optimization and define your optimization goal. So this is for the live presentation. If you have maybe some further questions to us, then please contact us via email or also via telephone with this number. If you have any requests or recommendation, then please contact also us via email. And if you maybe need some helping hands for your simulation daily work, then you can also contact us for some pilot project or CAE consulting. And so I would say thank you for your attention.